In Unit 1, we're going to focus on sets of numbers, properties, and operations with numbers. So some of the different objectives down here, the first thing we're going to really look at is the real number system and just being able to classify a number, looking at prime numbers, composite numbers, some different properties, and then we're going to go back and we're going to look at some basic operations. So we're going to look at operations with fractions, decimals, and being able to do those operations without a calculator. So for this unit, we won't be using a calculator. We need to go back and make sure that we can do all of those skills by hand. So before we get to the operations, this first lesson is going to focus on the real number system. So just looking at numbers. So like I said, we have really two number systems that you've heard of. The real number system is the big category here. Pretty much every kind of number that you've seen throughout middle school and high school math, where the other type of numbers that you've heard of probably in Algebra 2 are imaginary numbers. So those are those numbers with I in them. So imaginary and real numbers don't overlap. So if you look at this visual here, you have your real numbers and then you have your imaginary numbers, two totally separate categories. So these are your examples like 3i, 2 plus 5i, things like that. So anything with I in them is an imaginary number. And then a real number is pretty much everything that you've seen up to this point. Any other kind of numbers, as long as they don't have an I in them, it's a real number. So like radicals, fractions, decimals, negatives, positives, all of those numbers are real numbers. So if you notice, the real number system has all of these other little boxes in here because the real number system has other subcategories. So once it's a real number, there's two differences here for real numbers. It can be rational or it can be irrational, but it can't be both. So the next category that we're going to look at is rational versus irrational. So we have our rational numbers. It's the next subcategory, and irrational numbers. So a number can't be both irrational and rational. It's one or the other. So both rational and irrational, though, do belong to the real number system, but a number doesn't overlap. It's either rational or it's irrational because there's no overlap here. So if it's irrational, that's as far as it's going to go. So basically, if it's a messy decimal, so no pattern, so like pi is an example, or like the square root of 2, it just comes out to be a messy decimal, that's going to be irrational. Where rational numbers, I think of it as like a rational person. It's a nice decimal. It has a pattern to it. There's some kind of consistency. So rational numbers are things like fractions or repeating decimals or decimals that have patterns, positive, negative numbers, all of those kinds of things. So inside of rational numbers, the next subcategory is going to be integers. So integers include negative and positive whole numbers. So basically like -5, -4, -3, -2, all the way up, and including 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. All of those whole numbers, but they're also negatives. Where the next smaller category is going to be whole numbers because whole numbers start at 0. So whole numbers in the next category. And then the smallest category here is going to be the counting numbers, or sometimes called natural numbers. So counting numbers, or you can refer to these as natural. These numbers are going to start at 1. So basically, that's the smallest subgroup. So if we're looking at starting at 1 and going up to positive infinity, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not including any decimals, just going on forever, that's counting numbers. Counting numbers are inside of this whole numbers box because whole numbers include the counting numbers. So this is like saying 1, 2, 3, 4, 5, 6, 7, dot, 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 plus 0 is also included. So whole numbers, the only new number in there is 0. Where integers include all of those numbers, the 0, 1, 2, 3, 4, 5, and so on, but they also include the negatives. So that's why these boxes here are inside of integers. And then rational numbers include integers. So rational numbers include all of those negative and positive whole numbers, but rational numbers include more. They include those decimals that end, or the decimals that have patterns, or the fractions, that kind of thing. Where irrational, remember, completely separate, don't overlap. Irrational, or like an irrational person, is all over the place, no pattern, just like irrational numbers. The decimals are messy. There's no pattern to them. So let's just write down a couple examples down here. But I want you just to kind of understand like the whole visual behind this, how one of the sets is kind of like a subset of another. But let me give you some examples. So all of these down here are coming from the real number system. So these are all real numbers. These are just the different categories. Imaginary numbers, I gave you some examples, but we're really not going to focus on those, especially for this first unit. The first unit's really on the real number system. We will come back and talk about imaginary later on, but not for right now. So here's all of your real numbers. Um, and let's just go through and give some examples so it's easier. So counting in natural numbers, those are the numbers that start at 1 and they go up. So 1, 2, 3, 4, 5, and then so on. So dot, dot, dot. And then whole numbers, the only difference is they start at 0. So 0, 1, 2, 3, 4, 5, and so on. And then integers. Integers include all of those negative numbers. So I'm going to put dot, dot, dot on the left. And then I'm just going to write -3, -2, -1, 0, 1, 2, 3, and I'm going to do dot, dot, dot. So basically, this is showing that they go on forever from negative infinity all the way up to positive infinity. They just don't include any decimals. And then rational numbers. These are the nice numbers. So I'm going to write nice decimals underneath. It's not really mathematical, but it gives you a good idea. So nice decimals, as opposed to our messy decimals for irrational. So whenever you have a fraction, you can always turn it into a decimal and see that, okay, it's a nice decimal. There's going to be a pattern, or it's going to end, if you're not sure. But really, rational numbers are always going to include fractions. So you can add that here too. So some examples: 3/4, that's a good fraction. Square root of 4. If I take the square root of 4, it comes out to a whole number, so that's rational. I could say 1.232323, so on. There's a pattern, 2, 3 repeating. So that's irrational, because you could turn that into a fraction. Something that ends, so like 1.5. That's a decimal that ends. But remember, we also can include the negative numbers. We can also include any of these numbers up here. Because remember that these are all subcategories of rational numbers. So rational numbers include all of those things. And then the irrational are the ones that are completely different. They have their own category in the real number system. So like the square root of 2, if you were to put that into a calculator, you would get a messy decimal. There wouldn't be a pattern to it. Pi. Pi is a messy decimal. There's no pattern to it. We have, let's say, 0.346925 821 dot dot dot. It just keeps going. It's messy. There's no pattern. There's no way for me to describe that pattern to you. So this would be irrational. So there's some different examples. So let's look at some other types of numbers that are important here. So the next thing that we want to look at is a prime number versus a composite number. So basically, a prime number is any whole number greater than 1 that has exactly 2 divisors, itself and 1. So let's write some examples down for this. So some examples are going to be, starting at the smallest one is going to be 2, because the only number that will go into 2 is 2 and 1, so it's self and 1. The next one would be 3, 5, 7, 11, 13, 17, 19, 23, 29, and there's going to be other ones that just keep on going up. But these are probably your most common ones because they're the smaller ones. But any of these numbers, if you pick any of them, so let's say I pick 13, there's no other numbers that go into 13 other than itself and 1. So the only way I can get 13 is 13 times 1. Same with any of these. And there's more, you just keep going with it. So think of other numbers that only have divisors of itself and 1. Where a composite number is more commonly the numbers that we use, um, for factoring and that kind of stuff because they have more divisors. So a composite number is any whole number greater than 1 that is not a prime number. So that means it's a number that always has at least one divisor other than itself and 1. So, an example of this, basically any of the numbers that we skipped here, so it's got to be greater than 1, so any of the numbers that I skipped as a prime number would be a composite number. So if you look, 2, 3, okay, I skipped 4, well, 4 has other divisors other than itself and 1, so I have 4 times 1, 2 times 2 gives me 4. I skipped 6, so that has other divisors other than itself and 1, 2 and 3, 1 and 6. I skipped 8, 9, 10, 12, 14, 15, 16, 18, and so on. So basically all the numbers I skipped. So any of these numbers have other factors other than itself and 1, which is why it's considered a composite number. So let's do a couple examples that kind of use these ideas. So this first example is just to come up with one prime number and one composite number, and I'm just going to kind of justify why that's the case. So my example of a prime number, I'm going to use 43. And the reason is because if we were to break this down into its factors, well, the only numbers that multiply to 43 are going to be 43 times 1. Okay, so 43 is prime because its factors are itself and 1. Where if I look at a composite number, how about 12? 12 is my favorite number, so I'll go with that. So composite, we have 12. I know that this is composite, or I can justify it as being composite because, first of all, I think of any ways that I can break this down. So I'm thinking I could do 3 and 4. Some of you might be thinking 2 and 6. 1 and 12 you can, but it's not really going to do much for you because let's just say we want to break this down into what's called prime factorization as far as we can break it down. So I can break this down as 3 times 4. And then what happens is I look to see, okay, can I break these down any further? Well, yes, I can break 4 down further. I can break it into 2 times 2. So I kind of did two things here. So first of all, I know that 12 is composite, so let me write that. So 12 is composite because 3 and 4 are factors, which really means because it has factors other than itself and 1. But I also can break it down because I'm looking at the next example, the prime factorization. Because I went further with this 4, because 4 is a composite number, I can continue breaking that down into a product of its primes, which basically means basically keep factoring these or keep breaking down these composite numbers into its factors until you only have prime numbers left, and that's called prime factorization, or breaking a number down into a product of its primes. So 12, if you look at what we're left with here, we're left with a 3 is prime, 2 is prime, and so is 2. So I could say that 12 is really equal to these three numbers being multiplied together. So 3 times 2 times 2, because those are my remaining prime numbers, which if you check it, 3 times 2 is 6 times 2 is 12. And this is called the prime factorization, or also known as the product of its primes. So that's what we're going to look at on the next one here. So you can take any composite number and always rewrite it as a product of its primes. And basically, you just have to get down to the primes knowing it's a prime number by saying, okay, well, it only has factors of 1 in itself. So this last example that we're going to look at um, is basically taking what we did in this previous example, and we're going to take 60 and we're going to write it as a product of its primes. So basically this means prime factorization. So we're going to take 60, and when you do prime factorization, you don't have to worry about what factors you start with. You never want to start with 1 and 60 just because 1 and 60 is not going to get you anywhere. It just gets you to 60 again. So basically any number that you can find, or any two numbers that you can find that multiply to this is going to be fine. So whatever you want to start with, you could do 2 and 30. I'm going to do 6 and 10 because that's the first one that came to my mind. But if you did 2 and 30, that would be fine as well. So then when I get to 6 and 10, I realize that these are still composite. So that just means I got to break these down further. So 6 is going to get broken down into 2 times 3. And now since those are prime, I'm going to go ahead and circle them. And then I have 10 can get broken down into 2 and 5. And those are both prime. So now if I want to write 60 as a product of its prime factors, I basically just multiply these out. So 2 times 3 times 2 times 5 would actually give me 60, because this gets me 6, this gets me 10. 6 times 10 is 60. Now to clean this up a little bit, anything that's the same, instead of just writing 2 times 2, we can write it with an exponent. So instead of 2 times 2, I'm going to write it as 2 squared times 3 times 5. So this is actually how I want to represent 60 as a product of its prime factors.